Hi, everyone. So my presentation is on the history of fractals and their important elements. Um, Throughout the presentation, we'll just dive deeper into the fascinating world of fractals and explore not only their mathematical foundations, but also their occurrence in nature. We'll start the presentation by going over the history and how they are significant, and then also highlight Mandelbrot, who created fractal geometry, and then his contributions when he brought geometry back into the spotlight, into the mathematical world. We'll also go over the concept of fractals and examine some different famous examples, such as the serpentic triangle and the Mandelbrot set, to be able to illustrate how infinitely complex they are. And then we'll go over fractal dimensions and how those dimensions are actually between whole number dimensions. And then we'll use some applications and explore applications of fractal dimensions by referring to Mandelbrot's How Far is the Coastline of Britain, and then insights also from the book The Heart of Mathematics, An Invitation of Effective Thinking. So to start off, um, Bennet B. Mandelbrot actually founded fractal geometry in 1982. When he published a book, The Fractal Geometry of Nature, and just showing readers that in nature and mathematics, we see patterns all the time and on different types of scales. He was born in Poland in 1924, and at the time, Poland was under the influence of Nazism, so his family eventually left for France in 1936. He started to pursue his education, earning a doctorate at the University of Paris in 1952, and then eventually he retired in 2005 at Yale University. Mandelbrot died of cancer in Massachusetts on October 14th in 2010. He brought fractal geometry to mathematics because the Renaissance saw geometry um, as the forefront, but that was put on the back burner actually when much of the 19th and 20th century saw algebraic representation instead. Um, and then Mandelbrot just wanted to show that with the concept of geometry, we could bring back connecting mathematics to the world and nature that we live in. So that's why he wanted to bring it back. So, what is a fractal? Well, fractals are objects of the mind whose complexity continues to provide revelations and additional wonders of ever increasing magnification. Whether fractals are in nature or mathematics, they're infinitely complex. And in each fractal, there is an infinite amount of detail. So that's kind of where the infinitely complex comes from. Um, and this just means that if you examine a fractal, you'd see more detail the more deeply you look at it, or the more you zoom in on it. Fractals are created by a mathematical process in an ongoing loop where each part resembles its whole. The infinite complexity of a fractal is computed by a fractal's dimension that we will discuss just later in this presentation. So, nature's fractals. Um, Actually, Dave Feldman from the College of the Atlantic stated that fractals are all around us. They're in trees, mountain ranges, river deltas, and so on. Um, And this just makes sense because it's a simple iterative process, repeating, folding, or branching that can produce a fractal. So Feldman stated that. So in an article by Michael Brooks, who is a new scientist physics consultant and the author of the book The Math That Made Us, just tells readers that lungs are actually a fractal as well. And this is just because to me of the need to maximize the surface area while minimizing the space that it takes up within a human body. Um, so the surface area maximization exchange by exchanging oxygen and carbon dioxide efficiently and branching patterns within the bronchial tree efficient efficiency in the function of airflow and distribution of air. Um, the other one that we see in nature all the time is actually snowflake. So, and we'll discuss the Koch snowflake later on, in the coastline of Britain, which is also seen in nature. If we think of any snowflakes, or if we've ever seen one, we see that we have a consistent pattern that forms a unique element made in nature. Every branch or segment of a snowflake will be identical to every other branch or segment. And if we look at the rigid lines of a border or a coastline, it becomes more complex when we zoom in on something that of that nature, and it becomes easier to find its measurement, whereas finding its measurement like fully zoomed out, we won't be able to account for all its jagged lines and edges. So some fractal examples, first we'll go over the Sierpinski triangle. Um, And the Sierpinski triangle is named after the Polish mathematician Wacław Sierpinski and is seen in many different Roman churches as their floor tiles. Um, he actually created it by taking one large equilateral triangle and repeatedly cutting out a smaller triangle in its center. As you can see how it's formed on the side here of the presentation. Um, And if you were to zoom out of this, then you'll see a series of infinite structure and it'll just last forever as you zoom out or zoom in. Um, the next one we'll go over is the Mandelbrot set. And as you can tell, it's named after Benjamin Mandelbrot. It's made of a complex number equation. It's z sub n plus 1 equals z sub n squared plus c, and it's repeated until the set either diverges infinitely, where the color in the figure is chosen based on how fast it diverges, or until it diverges and is represented in black in the figure. And that's how the Mandelbrot set was formed. One of the biggest reasons why mathematicians get baffled by the idea of fractals is not because of the numbers they contain or how cool they may look, but because of the dimension that they hold. So let's go over some fractal dimensions. So as we should already know, a line is one-dimensional, and a square is two-dimensional, and a cube is three-dimensional. But what mathematicians are so interested in with fractals is how fractals have dimension between the first, second, and third dimensions, even though it may be hard to visualize. We can think about how these dimensions of fractals show the complexity that they contain in the mathematical world or nature. So first we'll go over the Koch snowflake, which is a fractal curve. And to the eye, when looking at this fractal, you would think that it's one-dimensional because it's made of it's one-dimensional because it's made of a one-dimensional line segment. But most people would, but when looking at the Koch snowflake, it's so incredibly jagged when you look at the very bottom picture, that it might look fuzzy. And so maybe you would think also that it's two-dimensional, but it can't just be two-dimensional because since it's just made up of lines, and it's also can't be one-dimensional. So in the book, The Heart of Mathematics by Edward G. Berger and Michael Starbird, they talk about the definition of dimension for fractals and end up with the equation S to the d power equals n, where we have an object, so any object, and n copies of that object can be assembled to create the larger version, and S would be the scale factor of that largest version. This dimension formula can also be computed in a calculator to the following: D equals ln of n divided by ln of s, where ln is the natural log. So we can define the dimension, the given formula, where d is the dimension and of the object to be the power which we have to raise s to have it equal to n. So to go back to this Koch snowflake and look at this equation is used to find its dimension. And we will see that the process of this fractal starts with an equilateral triangle. The iterative process takes each side of the triangle and divides it into 3 equal parts, where the middle part is replaced with 2 sides of an equilateral triangle, creating a star-like pattern that is repeated infinitely. And by using the formula discussed, d equals ln of n divided by ln of s, where n is the number of self-similar pieces and s is the scaling factor, we will find that since each iteration divides a line segment into 4 smaller segments, that makes n equal 4. To find s, we will look at each smaller segment and see that it's 1/3 the length of the original segment. So that makes s equal 3. Then we're going to plug these values in. So we're going to have d equals the ln of 4, the natural log of 4 divided by the natural log of 3. And if we calculate that in our calculator, d, the dimension, will be approximately 1.2619. And this just verifies that the Koch snowflake is in between the first and second dimension. So it's not the first dimensional figure, and it's not a second dimensional figure, but it's in between those. So let's go back to the coastline of Britain that we talked about earlier. And we'll just show the difference between this and the Koch snowflake that we just reviewed. So if we look at the coastline of Britain, we'll see the same concept, kind of like the Koch snowflake, where we look at the coastline of Britain from afar and we see it doesn't look as complex as it would if we were to zoom in on it. And just see that if we zoom in on it, there's jagged corners and curves that you wouldn't see from afar. So to derive the dimension, we would use the same method as we did before for the Koch snowflake. But we would also see that if we were to take the measurement of the coastline in different ways, then it would be different. So if you were to measure the coastline in yards, you would get a large number. But if you were to measure the coastline in feet, you would get an even larger number because you're accounting for all those curves and edges in the coastline. So to accurately measure the coastline, we would also use the natural log of n divided by the natural log of s. And Mandelbrot actually measured the coastline at different scales, meaning in 1 kilometer by 100 meters by 10 meters, and differently you can kind of see in the figure on the side as well. So then he then counted the number of line segments n that were needed to cover the coastline at each scale. He determined the scaling factor s by comparing the different scales, and by finding the logarithm of the number of line segments n divided by the scaling factor s, Mandelbrot found the slope of the resulting line, and it gave a complex dimension. So he actually found the fractal dimension to be approximately 1.25, which, like we discussed earlier, we thought maybe the Koch snowflake was 1-dimensional or 2-dimensional, but it was actually in between those when we derived it from the formula. And as seen in this one as well, in the coastline of Britain, we may have thought it was 1-dimensional or 2-dimensional, but it was actually in between those. And through the formula as well, we found that the dimension was 1.25. which is slightly different from the Koch snowflake. So just a fractal overview. Um, we just in fractals are just a very underappreciated thing in mathematics and nature when showing just how complex they can be. Um, we also went over the historical contributions from the founder of fractals, Mandelbrot, and how he has shown the intricate patterns found in nature or derived in mathematics and testing our understanding of what we kind of already know about dimensions and geometry and just kind of furthering that. Um, we also looked at the examples of the Serpentine triangle and the Mandelbrot set. How long is the coastline of Britain and the Koch snowflake? And we just can see that some of the simplest processes can have infinitely complex structures. Um, we don't really see that sometimes until we really zoom in on something and understand its structure and the complexity it actually has. Um, and this type of complexity wouldn't be known without understanding that these fractals are derived from an equation that will continue infinitely. Um, we also kind of took a look at fractal dimensions and what kind of we have to understand about dimensions with fractals. And fractal dimensions develop appreciation by knowing that they highlight the challenges of our understanding of the first, second, and third dimensions. Um, Overall, this presentation was just meant to dive deeper into the fascinating world of fractals and just hopefully encourages you to open your eyes to new mathematical concepts and the beauty of the natural world around us. And hopefully you can now see fractals in nature and also fractals in mathematics and notice them and then just sometimes take a deeper dive into them and notice how complex they actually are and how beautiful they actually are. So thank you for watching, and that's my presentation on fractals and their history and their elements.